So, hello everyone. So today we will discuss the gated cross attention for depth collection completion. So let us start it. So first of all, we'll see what are the challenges which we have in recovering the dense depth. So in this paper, they used a data which is LiDAR, which is the remote sensing technique which we know already. So one complication with this was it usually used to be very sparse in nature. So most of the values are zero. So it is very difficult to extract the real distance measurement, which are very few in the data. And the second was the RGB images. As we know, they are dense and rich in texture, but they are noisy. So the task would be to recover like the full dense map from the sparse LiDAR input data, which is the distance measurements and also using the RGB data as a complementary one. So let us see this diagram, you can see like what initial approaches used to be like. We used to have RGB images, then the ground truth like for evaluation purposes and the sparse depth map, which we get it from the LiDAR data. So we used to have these RGB images, and based on that, we directly push it into give it to the sparse depth map, and they used to give the final projections and the depth map. But it used to be very weird and not accurate because we know the RGB images are very noisy in nature. So this was a challenge which we had. So we got it like the
Aditi,
problem is, yeah,
uh, yeah, I
yeah.
have a question.
Mhm.
What exactly do you
Yeah.
mean by recovering dense depth? What's the problem that you're trying to solve here?
So the problem is related to the correlation between the RGB data and the other dense maps. So the RGB data used to be having the local values, the color maps, and the dense depth used to have some values which are the distance measurements. So LiDAR data used to be the data which is comprising of the points, which are millions of points, and it used to be in the remote sensing area and autonomous driving. So it provides that dense depth, so that distance measurement, so how well it is. So both correlation is very important as we used to have in other domains like temporal and spatial. So there need a correlation between these two modalities. We can consider these two as modalities here.
Okay, so you are
Did
trying
you
to
get it?
map the
Yeah.
RGB data to the depth map that you have from
Yeah,
LiDAR.
yeah, yeah,
Okay,
yeah, exactly.
okay.
So the problem is like the asymmetry between these two modalities. So the first is RGB and the second is the depth. So which is highly sparse, and RGB is having the problem that it is noisy. So we need to have a efficient cross model fusion, which is like as attention based to maintain both the local and the structural accuracy and also the global scenario, right? So
एक सेकंड
we
अदिति
had mhm,
can you go back हाँ ये
yeah, yeah,
lidar is basically a sensor ना जो basically
light
हमें
detection
light
and
पे उसमें
ranging.
वो reflect
Yeah,
होके वापस आती है so we know what's the depth.
yeah,
So
yeah,
मतलब I
yeah.
didn't understand what do you mean by sparsity here? Can you explain why is it sparse? What exactly do you mean by sparse
Why
when it
exactly it is sparse? Sparse means like most of the values are not there because they are long-ranging data and might be missing. So usually the nature of this data is like it is highly sparse in nature and very few information are there, but those informations are really important. So that is why we need to preserve those importance, important features like the informations
Maybe
are.
maybe it's like that because if you are on an open
Mhm.
road, most of the light will not get reflected back to the
Maybe,
sensor.
and yeah, yeah, it is laser based, so maybe. But the nature is like they are really highly sparse.
okay got it. हाँ this makes
Yeah,
sense अगर हम
yeah,
autonomous driving देख रहे हैं so some most of
Hmm.
the light will not come back हाँ
yeah, yeah, yeah. This may be.
uh, ठीक है you can continue these things.
Okay. So this is like the basic idea which they have proposed in a very simple manner. We'll see the architecture next. So the First is like the input features, which we know RGB and the depth tensors or maps. So we'll go with that gating mechanism, which will decide the useful signals, and then we'll fuse it, like combine them and loop it over the process. Like we'll take the feedback and improve the functioning. So what contribution it does have? So the first, the paper provides is like the gating confidence propagation. So they use the gating uh, phenomena in which they take the important features, like we have two RGB and the dense maps. So it provides a kind of a gating, or a gating means like a control for getting the propagation of this data. And the second is the transformer integration. So they also integrate a transformer for global fusion, and they use it at the low dimension for like computationally costly, it should be lower. So for that reason, they are doing it at low dimensional scales, and hyperparameter tuning just for the optimization purpose. So this is the main architecture which they are having. So first is the dual encoder. So this image first is the RGB image, and the second one is that depth map DS sparse one. So they had two encoders separate in this architecture. So first is the RGB encoder, and second one is the depth encoder. And they first of all put some convolution errors and the deconvolution layers so that they can downsample the images. And here they do the bidirectional kind of attention mechanism. So here the green ones which are here, they are gated cross attention. So we'll see what actually this is working, but the arrow which we can see there is the plus one is like the residual addition. So simultaneously at each step we are adding from the RGB data back to the depth one and depth one to the color ones. So they are equally in vice versa way, they are updating each other, and at the end they both are going to the transformer mechanism, which is like self attention based for getting that global idea, global context. They just apply it once at the end and then integrate it and then again upsample it and give the final image. So there is a unified decoder which generates the final dense map. So this is the way like how they go, like the dual encoder, then the global fusion, then gated cross attention, and the signal decoder. So this is the same thing.
एक second, Aditi.
Yeah,
This is an
yeah.
LSTM cell ना, ये जो बीच में लगी हुई है, that's an LSTM cell, I think. तो इसकी
This is yeah, cross attention. Yeah,
but why this is an LSTM cell, right?
yeah, kind of you can say.
No, I think it's exactly like the LSTM cell. So why is it required here if we
Mm-hmm,
are doing self attention आगे जाके? तो
mm-hmm,
हम लोग को basically for this RGB image and lidar inputs that we
mm-hmm.
have, we don't need to do anything here, right? If we are going to apply the self attention later in the transformer phase, so why do we need to apply this LSTMs or whatever
Yeah,
computation there? Is there any
yeah. So
reason?
here, yeah, here it is for the local perspective. Here we are seeing like the minor details which we are having and for correction purposes. So we'll see in the next slide like why exactly it is over here, how it is correcting the error which are having in the RGB part and which are in the uh, our other depth maps. So they are correlated to each other to remove the errors which we are having in both the sense. And that corrected ones will go to that transformer, and that will take the global context at the end, and which will at the end give us the corrected ones, like the correct network depth map. I think it is clear.
थोड़ा थोड़ा आया समझ में, like you can
Yeah,
continue. I
we'll
will
see.
देखना
We'll see the algorithm. I think that would be the thing you will be getting. So
ठीक है.
in the first step, what we do is first we initialize the confidence weights. So we are having the this main equation. So YT is the depth feature and XT is the color feature. So what we'll do, like just simply do the convolution. So sigma is used like a function which is giving the value between 0 and 1. So we'll use it for just getting the YT, correct YT, where the depth is confidence, like the confidence score, and multiplying it with the XT, like the color feature. So we'll get the vector, which is like the combination of XT and YT, and where the depth is confident, right? The second step is optimizing the color feature. Now it comes to the main part, like why we need that attention over there. So we are having PY, which is a sigmoid function, which we are taking on YT. YT is our depth map, right? So that would work as a gate, which will see like where the depth base is actually correct. And IY we are taking as 10H, which will give us the correct values, because we know 10H will give us values between -1 and 1. So either it would be addition or subtraction based on the need. So at the end, we get a corrected color vector, color feature, UT, which is like we'll add the previous one and the multiplication of these both. So this is kind of a correction, error correction in the color feature vector. I think it is clear. If it is not, this,
Yeah, can you go back to the previous slide first?
yeah, yeah.
Okay, so this can you give me an overview of the steps? What are the steps we are taking?
Yeah, so these are the two inputs we know, right? XT and the YT. So YT is our depth feature, XT is our color feature, right? We are taking the sigmoid, we know YT, which is the depth feature. So based on depth feature, we'll see where the confidence is higher, because sigmoid will give us a value between 0 and 1. So
Yeah.
obviously the higher values are good, right? And the lower are the bad ones,
Okay.
right? So we'll multiply
What
it
is
with, yeah.
WF here?
WS is like the parameters, so WF and BF like bias and the weights, right?
Yeah, that's right. But WF is
Mhm.
from which part of the network that you showed before? Is
In
that
the
from
yeah,
the depth one?
yeah, yeah. It is
Okay.
a convolution layer, so yeah,
Okay. So these scores are calculated in these are the green blocks that are in between.
yeah. These no, these are these ones.
Okay. So this that operation that you're describing to to get the attention,
Yeah,
the
yeah.
score, the
This
confidence
ones,
score.
green ones.
So
Yeah,
so the green
yeah,
block in between is the one is that equation.
yeah. The smaller part of that. This is like the black and the red ones. You can see
Hmm.
small that part. It is. Yeah,
Okay.
yeah.
Okay. Now it's a bit
So it
clearer.
is like two parts over here. You can see one first and the second, that blue and black. So we are discussing about that first part over here, there. So we are getting a corrected color feature over here by using the depth feature. So we are taking
Okay.
the depth feature, we are taking the 10H so that we can get like what are the corrected values. And based on that corrected value, we are refining our color feature, right? Because we know color feature is having some issues, which is having noise, right? So we need to
Mhm.
prevent those noise. So for that reason, we are using depth feature, which is YT. So we are computing that PY as a gate. We are getting IY, which is the corrected value, and based on that, we are getting UT, which is the updated color feature, right? I think it is
Okay.
clear.
Okay.
Yeah. Yeah.
Mhm.
So we have optimized our color feature, which is the step two. The third is optimizing the depth feature. So here there is an interesting part. Like what we are doing, it is bidirectional. So first we have corrected our color feature. Now we'll correct our depth feature, because depth feature is also having a lot of sparse value. So there are missing holes are there. So we take this part. So OY is again we are taking that the previous ones in the similar fashion. We are taking the gate which will control the output, right? The corrected ones. IY will be the 10H, which is -1 and 1. The values would be between that. And UT is a corrected color feature, right? Now we'll give UT here because we know the UT, which is the color feature, is correct now. Based on that, we'll evaluate the correct values, and that will multiply with OY so that we'll get a correct depth feature. So here we have updated the depth feature based on the values of the color feature. So now the process goes like we have initialized the confidence weights, we have updated our color feature based on the depth feature, and then we are using the corrected color feature for updating the depth feature. Now, yeah, this is the whole process goes. Like now, the fourth and the fifth step are the residual fusion. We'll add the residual so that we don't have the issue of vanishing gradient and that stuff. So we are just adding the actual inputs like x, t, and yt to the corrected ones. And we keep doing it from half to 1 upon 16 resolution, like vertical direction, horizontal direction at different multiple resolutions. We keep doing it. And the corner size they have taken is 1 cross 5 and 5 cross 1. And this is an iterative process. The loop goes on. So initializing this process we have discussed. Second part, which is like updating the depth feature. Third is the updating. uh, Second is color features, and third one is depth feature based on the corrected color features. Fourth is skip connections and residual vectors, which we are adding. And the fifth one is like the iteration process. So yeah, so this is how the work process goes. So is it clear?
Aditi just
Yeah,
had one question.
yeah,
So,
yeah,
for the color features, we are sort of incorporating the depth information somehow, right?
yeah,
And vice versa. For the depth features, we are somehow incorporating the color features.
yeah, yeah.
Uh,
So it is that bi-directional process. So based on the depth feature, we are correcting the color features, and the color features which are now corrected in step two,
yeah.
we are using those in the step three. Yeah,
Yeah.
yeah.
So, is the idea here that you
Mhm.
somehow want the model to be able to go from the color features to the depth features? Like, I wasn't quite sure what the objective here is.
Yeah. So objective is like to have the actual depth map, which is correct, right? So we know our data is having issues with the RGB data with the noisy values, and we know the depth feature is also having some holes. But we know that the depth features where the information is there, it is authentic, it is actually correct. So based on that, we are correcting our color features because we know something is authentic over there. And then once that is correct, so we know we have a color feature. Based on that, we are trying to fill those missing values which are there in our depth maps. So in this way, they are doing in iterative way so that we can get a final depth map, which is actually having some sense related to the actual one. So this is the process how they are going for it.
I see. Yeah. Okay. Thank you. That makes sense.
Yeah,
Yeah.
maybe I can make a comment on that. So
Yeah.
it's like one you have one RGB image and one depth map.
Hmm.
The depth map has no
Yeah.
understanding of the scene, and in
Yeah.
RGB you have the understanding of the scene because of the colors and everything, the objects that you can see. Depth
Hmm.
map
Hmm.
just gives you just depth information. So you have
Yeah.
to somehow combine them to get
Correlate.
the whole scene
Yeah.
understanding, the complete scene
Yeah.
understanding.
Yeah. Yeah. It is kind
So
of a correlation between those two modalities, which are making some sense
mhm.
once they are connected to each other, right?
Yeah.
Yeah. Yeah.
Acha,
Yeah.
one more thing.
Mhm.
My vision transformers they are not using, right? So they're just doing a simple
No, no.
convolution operation
Right
to route.
now, up to this point, they have not.
अच्छा
No, they have
और
not.
मैंने
And
देखा
also,
था
the next,
कि
they are just using transformer. Yeah, not a vision transformer. Yeah.
हाँ क्योंकि मैंने देखा इसमें like they're just converting it to a simple
Yeah.
uh,
Yeah. Yeah.
vector or small image.
Hmm.
हम्म. Is
Yeah.
there any
True.
reason they haven't used vision transformer? क्योंकि मेरे हिसाब से तो स्ट्रेट फॉरवर्ड चॉइस तो वही होती राइट ये थोड़ा कॉम्प्लिकेटेड लग रहा है मेरे को so have they mentioned
Yeah, they have complicated it, I think, for better results, for better local awareness, and also then the global awareness. So
अच्छा so they
they
haven't
want the
mentioned
control over the modalities because the situation is over here is like both the data are having some issues and which are very minor. So that is why I think they have used that gated cross attention so that we have the control over. what we can take and what we are leaving over here.
Mm. But they haven't specified actually why they have
Yeah,
chosen
yeah,
to use
yeah. They
convolutions instead of
haven't.
vision transformers.
Yeah, yeah.
Yeah, I thought like
That
that would
is
be a
not.
straightforward choice ना मतलब देखा जाए तो
Yeah,
डबल
Hmm.
बेस साथ में पास कर दो
yeah,
विजन ट्रांसफॉर्मर है
yeah.
और सब कुछ हो जाएगा
Mm-hmm. Mm,
ठीक है
yeah, that makes sense.
definitely
Yeah, so this is like the Transformer Global Fusion. So that we have, let me go back.
Is it because
So
of
the last
maybe
part,
they're not using
yeah.
transformers because of the
Mhm.
latency in processing the input?
Yeah, this is a good thing. Yeah, this is optimized in that way. Yeah, this might be
लेटेंसी
a
की
reason.
होगी तो
Conv
इसमें तो एक साथ जाएगा
convolutions
ना
are convolutions are
Lighter.
faster as
Yeah.
compared to
Mm.
VITs,
Yeah, yeah, yeah.
right?
Mhm.
That's what I think maybe.
Maybe, yeah, because they have used just one transformer at the end and they are not using over here. So maybe, yeah, the process they wanted to be optimized in that way.
नहीं कॉन्वोल्यूशन कैसे हो सकता है फास्ट ट्रांसफॉर्मर पे ट्रांसफॉर्मर पैरेलल चलेगा
Hmm.
कॉन्वोल्यूशन इज सीक्वेंशियल सॉरी वीआईटी विल पैरेलली वो डिवाइड करेगा ना 16 by 16 जो भी है एंड इट विल
Hmm.
बेसिकली जस्ट run everything parallelly ना all the attention सब कुछ
Yeah.
so naturally of course transformer will be faster 100%.
Yeah, but computationally it will be expensive a little bit.
अब ये मॉडल इतने बड़े मॉडल्स आई थिंक ट्रेन हो रहे हैं रनिंग कंप्यूटेशनल
Mm.
इशू होगा
Hmm.
क्योंकि
Okay.
कॉन्वोल्यूशन इज सीक्वेंशियल ऑपरेशन ना you cannot get
Hmm.
Hmm.
Yeah.
nth stage without processing n-1 stage
Yeah.
हाँ
वीआईटी can just do पूरा parallel कुछ नहीं करना
Mm.
हाँ बट
Yeah.
वही इसमें इन्होंने अपने पेपर में दे हैव गिवन ये टाइम कंपैरिजन ना इसमें
हम्म
कि मतलब they are showing कि how much time it takes for
Yeah. Yeah. Yeah.
their
Time
algorithm to
aspect
run.
they are
So
giving.
that's why I was thinking कि maybe because of getting
Mm.
this time constraint की वजह से they want it faster.
Mm.
हम्म
Maybe.
और उन्होंने कहीं मेंशन किया नहीं ना वीआईटी के बारे में इस पूरे पेपर में
No, no, no. They have not mentioned
Hmm.
it.
मे बी दे हैवंट ट्राइड और पता नहीं जो भी
Yeah. Yeah.
I think
That may
here
be addition. Yeah.
objective is just the self-attention, right? They just want to get the global context over here.
Yeah.
So
Yeah.
I think they might have felt like, given how well established CNNs are for computer
Mm.
vision, the easier choice, like you said.
Maybe. Yeah. The basic one started with that. Okay. So is there any doubt still?
No, you can move forward.
Okay. Okay. So uh, now the last part is that self-attention that transformer will discuss in the next one. So yeah. So this one is now we know we have updated and the final FI and FD. FI is like the images, RGB, and D is the depth map. So we'll add that position embeddings because we know we need in the transformer this one. So and then we apply the self-attention over here. So we know this equation like Q KT upon root 2K in dot V. So queries, key and values, K and B, DK is the dimensions. So we are simply, this is a very simple process in which we a normalization layer they apply and the self-attention mechanisms keep moving and at the end they apply MLP, which is a multi-layer perceptron layer, just over here at the end and this process goes back. So this is a process and they do it at the low resolution. So the reason which they have mentioned is like they wanted to be less computationally costly, and that is why they are using the low resolution over here. And so this global fusion basically includes the multi-head self-attention followed by the feed-forward network and normalization. So feed-forward is like by this MLP layer over here. So in this way, it gets the spatial relationship over the network. So this is the global fusion. Then the loss function. So
Okay, so
they
this was
are
self-attention, right?
mhm,
This was self-attention.
yeah,
There
this is
was
self-attention. Yeah,
Okay,
yeah.
so
This
you
is
are giving the maps from
mhm.
image and the depth that
Yeah,
you
and the
get
depth. Yeah,
in, yeah,
yeah,
both of them together in query key
yeah,
and values. So there
yeah,
is no
yeah,
cross
yeah,
attention. Okay,
yeah. There's just that's it.
okay,
So, and this is loss. So they are computing this kind of loss. So this will take each and everything. Like deep red is like the depth, dense depth values, so which are predicted by the decoder, and DGT, which is like the ground truths, and they are squaring it and multiplying it with the bool greater than e to the power minus 3 is like the values which are greater than 0.001. So they are kind of limiting the values over here. And alpha and beta are utilized for controlling the training stage and implementation. So this is how they have computed their loss for the training process. And at the end, they have used this hyperparameter tuning. So we know we had a lot of computations over here. So RayTune is the method like automated hyperparameter tuning library. So this is they have implemented. So in this particularly, they have used HyperOpt, which is machine learning algorithm, um, which is working on the Bayesian optimization algorithm. And as a stopping strategy, they have used a scheduler which is async hyper bend. So we can see in the diagram they have described it a little bit. So RGB and the depth they are working in like interacting with each other with the gate, and here there are the possibilities which are shown with the help of that tree, like 4 to the power 5, 4 to the power 5, 3 times, and then the 3 times. So here 4 comes from these four values RGB like 1, 2, 3, 4, and 5 are the values they have taken, and 3 is batch size, like 3 numbers are there. So they put it into the algorithm, which is the hyperopt, and that takes help from the band scheduler, async hype band scheduler, which is really important for removing the bad runs. So it automatically detects the loss where the loss is really bad. So it removes them automatically, keeps checking it, and it gives back the algorithm so that it keeps checking it. So in this way, they are optimizing their parameters and the iteration numbers particularly in this manner. And experimental setup. So they have used the data KITTI depth. This is a benchmark data set. So they have autonomous driving scenarios with the LIDAR data, so light detection and resolution, and then hardware PyTorch. They have used NVIDIA GPU. Baseline comparison they have done with the existing ones which have done work in this field. So CSPN, convolutional spatial propagation network, pyramid encoding network, and grid network. So these are some ways in which people have experimented in this. So uh, and for evaluation, root mean square error and MAE, which is mean absolute error. So these are some quantitative results what they get. So they have shown that the root mean square error is decreased. So these are the formulas for them. So root mean square error, mean absolute error, like absolute, and then 1 upon n. 1 upon n is like the h into w, which is like pixel values and number of pixels, and the root mean square error of inverse depth. This is the formula for that. So they are taking inverse, then they are absolute taking and square and 1 upon n, and then at the end they are taking the root. So these are the two
Aditi,
values. Yeah.
एक question है how
Mhm.
do they generate the ground truth here? So what is the ground truth? मतलब किससे compare करते हैं generated depth map को? Do they have the
Ground
actual depth?
truth. Yeah, the actual depth map they have the ones which they know actually those are correct. So this is a kind of supervised that thing, so they know the actual ones,
हाँ,
right?
so how do they create those? Like if we have seen ना कि lidar भी काम नहीं करता,
Mhm.
RGB भी नहीं करता, so that's why we are making this
Mhm.
network. So how do they
Yeah.
generate those ground truths?
that is existing in the data. So
But वो data में आया कैसे? That's the
बनाया
main
होगा
yeah,
question.
that is something need to be like need to see that like how they have generated, but they have not mentioned it like how they have, but they know like there are ground truths already.
ये अब स्केल से तो नापा नहीं होगा ज्यादा कि हाँ भाई
Nah,
कितना दूर
yeah, that
कुछ तो
is
उस तरीका
something.
किया होगा
Hmm, that is something need to be checked. Yeah, I'll check it. Okay, so their performance is good. Like they have 6 times time decrement कर दिया है 0.14 से 0.047. So yeah, this may be something like they have used convolution and rest error भी काफी minimize हो गई है. And for discussion, we can see like strengths are like adaptive gating है, efficient design है, and automatic tuning है. We are having automatically hyperparameter tuning is going on. So weakness could be the cost compute. Like at the end, we are having that global attention, that transformer, which may add up some value. And they lack some uncertainty, like probabilistic. They are not doing anything. They are not uh, like predicting anything over here. They're just very fixed with their context. So I feel these are two weaknesses. And for research directions in this domain, so they can add like uncertainty aspect that we discussed. Second would be like the video-based temporal consistency. So they can add some other aspect, other data, video frames. So there will be temporal data as well. So prediction over time they can do, and multi-sensor fusion they can do. Like in place of like doing just input of the LiDAR, which is a depth map and RGB, they can add some data from the cameras to video camera also. So that will improve the actual outputs. So this can be some, these are some ways. And now the what are the broader application which we can see with beyond that depth completion. So this gated cross attention mechanism can be really good for many other applications like medical imaging fusion, like MRI and CT scan. So and any other modality, I would say like you are having two different modalities and you're working on the data and you want that correlation. So that gated mechanism will really help you to do that. You can control those parameters and work with that. So these are some application you can see: autonomous driving, perception, robotics, augmented reality, satellite imaging, etc. So these are some applications. These are some few references like the data and the research paper. That's all for today. Thank you so much.
Thank you, Aditi. Uh,
Yes.
So,
Yeah.
so for वो so how they get the ground truth उनकी website पे they've written accurate ground
Mm-hmm.
truth is provided by some Velodyne laser scanner and a GPS localization system. So there
अच्छा
are some
Okay.
advanced technologies there to get that ground truth.
To get that data.
Mm.
Okay.
तो ये टेस्ला वगैरह
Interesting.
क्या यूज करते होंगे मतलब डेप्थ मैप्स के लिए डू यू हैव एनी आइडिया जी लाइक दे हैव ऑटोनोमस कार्स
Mm-hmm.
बहुत टाइम से चल रही है
Mm-hmm.
तो
Mm-hmm.
डेप्थ मैप
Yeah.
उनके लिए क्या क्या यूज होता है एग्जैक्टली लिडार तो होता है
Yeah,
आई थिंक लिडार पे लगा होता है उसके
yeah.
अलावा
Radar तो होता है.
I think इसमें ये
Mm-hmm.
जो अभी जो ग्राउंड ट्रूथ कैप्चर कर रहे हैं, I think
Mm-hmm.
it will take a lot of time for them to actually get the ground truth. वो सारा डेटा कलेक्ट
Mm.
करके उसको प्रोसेसिंग पर डाल के उसके बाद they must get the ground truth, final ground truth. But
If I'm
Yeah.
not wrong, Tesla is completely vision based.
yeah,
There is no
completely
depth
vision.
sensor.
Mm.
अच्छा तो
Mm.
लिडार नहीं होता
Yeah.
उसमें
Nope.
ओके कंप्लीटली विजन बेस्ड तो यार which
That
is
is
basically
something.
It's impressive.
Hmm.
तो
Mm.
बहुत ही ज्यादा इंप्रेसिव है क्योंकि बहुत साल पहले निकाल दिया था मस्त ने राइट
Mm.
So how
Mm.
do they do that? Like, have they published any details? कैसे किया उन्होंने पूरा?
Mm-hmm.
I don't think so.
No idea.
That I have to check. Yeah.
I don't think they will.
Hmm.
Yeah.
That's that's the part of
Mm.
Tesla.
Mm.
पूरा vision based है तो it's really really impressive
That
मतलब
would
like
be innovation. So why will they? Like for now, I don't think so. They.
Mm. Hmm. Nice. Okay. So इस पेपर का टाइटल is very confusing. It's saying gated cross attention network. So that cross
Yeah,
attention gives you feeling कि
yeah.
इसमें कि cross attention का कुछ use होगा, but it's not that.
No, not
मतलब
cross attention. It is like what they are having the correlation between those two modalities.
yeah,
So, yeah, that
should be
RGB
something like
and
yeah.
yeah,
It shouldn't even be called cross attention, not even attention when you are doing that. It's because
yeah,
that's not attention mechanism that's out there.
mm,
It's something different.
yeah, that's true.
Hmm. Okay. Hello, thank you, Aditi, for such a good presentation.
Thank you so much for
Thank
having me.
you, Aditi. It's a great
Yeah,
Thank
to
you.
be
presentation.
Amazing
here.
presentation.
जस्ट एन एडवाइस बहुत
Mm,
तेज बोलती हो तुम प्लीज
हाँ.
mm.
अभी थोड़ा like it's
It
good
was
to
fast.
pause बीच बीच में and ask everyone